Good afternoon, everyone. Myself, Hemalatha from Laxman Reddy Institute of Technology and Management. I'm a faculty in applied physics. So, I've been teaching you the topic lasers and fiber optics, and we have covered some of the topics till now. And this is my fourth lecture. In this fourth lecture, I will be covering the topic which is called as the carbon dioxide laser. We have already covered two lasers. One is ruby laser, second one is helium neon laser. And the third type of gas laser, this is also one type of gas laser, molecular gas laser we call it as, that is carbon dioxide laser. Now what is this molecular gas laser? In a molecular gas laser, that is the lasing action, will be taken between the vibrational and rotational energy levels. So previously we were studying in ruby laser and helium neon laser in a normal manner. That is the excitation from higher energy state to lower energy state. And we used to show you how population inversion was taking place. Okay, and the output we used to find out. But whereas in case of molecular gas laser, here we will be studying about the vibrational and the rotational energy levels. Now, this is the first laser which was invented in order to study about this vibrational and rotational energy levels. Now, and it is a 4-level molecular gas laser. As in the previous classes where I told you, you need to write the introduction, which is in a very short form, you can write that one. It's a molecular gas laser, one thing. Second point, it is having a 4-level laser system, and vibration energy levels and rotational energy levels will be found here. And the type of pumping which will be used is the electric discharge pumping only. Here also we will be placing two plano-convex lens on both the sides of the glass tube, and then they will be providing us the optical resonating cavity, one of the component of laser system. Next, let us go for what are the different energy states which are present in carbon dioxide molecules. Each and every carbon dioxide molecule will have one center atom as a carbon atom, and the other two atoms, other sides of the carbon atom is being attached with two oxygen atoms, CO2 we will be writing. So, one center atom is carbon and the other two sides, one on right side, one on left side will be the oxygen atoms. Now, such a molecule, that is a carbon dioxide molecule, will be vibrating in 3 different modes of vibration. In 3 different modes of vibration, the carbon dioxide molecule rotates. And the 3 different modes of vibration are, one is called as the symmetric stretching mode, that is all the molecules symmetric. You know the meaning of symmetric, that is all points moving on a single plane. So here also the same thing, the carbon atom and the oxygen atom, two oxygen atoms, they will be moving, they will be rotating on a single plane. That we call it as a symmetric stretching mode. Next, bending mode. One atom will be bending with respect to the other two atoms. That is called as the bending mode. Next, asymmetric stretching mode. Asymmetric. One rotates in one direction, other rotates in the other direction. That is asymmetric. They are not in the symmetric way. They are not moving in a single direction. They are moving in different directions. So we call it as the asymmetric stretching mode of vibration. Now let us first come with respect to symmetric stretching mode. Now in this one, you can see the figure here. Carbon atom is which is present at the center. This is the carbon atom, and the two sides of the carbon atom is attached with the two oxygen atoms. These two are the oxygen atoms. Okay, now here, in this mode of vibration, carbon atom will be in rest position. That means it does not move, it does not rotate, or it does not vibrate. But both the oxygen atoms, which are attached to the other ends of the carbon atom, they vibrate in such a way that the vibration which is taking place will make in such a way that the two oxygen atoms will be approaching towards the carbon atom. That is what the mode of vibration which will be taking place in case of symmetric stretching mode. You can see both the oxygen atoms, they move towards the carbon atom. That type of mode of vibration, we call it as a symmetric stretching mode. That is, in this mode of vibration, carbon atom is at rest and both the oxygen atoms, they vibrate, which is approaching towards the carbon atom. So this type of bending, we call it as the symmetric stretching mode. Now second one, bending mode. Bending. The name itself is giving you bending. So let us take carbon atom is bending. Both the oxygen atoms are at rest. Only the carbon atom rotates here, vibrates here, and both the oxygen atoms are attached, which are present. They are at rest position only. You can see this figure. This is oxygen and this is the center carbon atom. So in this mode of vibration, both oxygen atoms and carbon atom vibrate perpendicular to molecular axis. You can say both vibrates, or you can say only carbon atom is vibrating. Only carbon atom vibration taking place, making the two other atoms, that is oxygen atoms, in rest position. Next, asymmetric mode of vibration. Asymmetric. The atoms are moving in different directions. In this mode of vibration, both oxygen atoms and carbon atom vibrate asymmetrically. You can see this figure. Now see the direction of oxygen atom. It is moving in one direction, and see the carbon atom. It is moving in the other direction. If I show you in the figure, the oxygen atom is moving in this manner. This is a carbon atom which is present, and this is another oxygen atom which is present. So this carbon atom moves in this direction, and the oxygen atom can move in this direction, or there is a chance for moving in this direction also. This type of mode of vibration, we call it as asymmetric stretching mode of vibration. Next, what is the basic principle involved in the production of lasing output? Laser output has to be produced. So what is the principle which is involved? So the laser transition takes place between the vibrational energy states of carbon dioxide molecules. In between the carbon and oxygen atoms, the lasing action will be produced. That means we can produce a laser output in case of carbon dioxide molecule. Next, what is the construction of this one? It consists of a quartz glass tube which is having some length, that is 5 centimeters length and 2.5 centimeters in diameter. And this glass tube is filled with a mixture of carbon dioxide. CO2 gas is filled in that glass tube. Now, in order to go for the excitation, in order to make this gas go inside the carbon dioxide gas to go inside the quartz glass tube, here also we are using some other supporting gases. That is, one is nitrogen gas and one is helium gas. Why? Because these two can pump the gases inside the glass tube very easily. That's why we are using these two gases as the supporting gases in order to make the carbon dioxide gas pass into the glass tube. Now, the terminals of the glass tube, they are connected to a DC power supply, because we have to give some energy, external source of energy. So that energy can be provided by using a DC power supply. And next, the ends of the glass tube, here they are being drawn by using windows which are called as Brewster windows. Why they are called as Brewster windows? Already I told you in the helium neon laser lecture. That means they are the windows which are specially designed at some inclination, angle of inclination is given, so that the gases, when they collide with each other, when we give them some internal voltage, then automatically the gas which is discharged, which is passing into the glass tube, the atoms will collide with each other. Here carbon dioxide gas is present, nitrogen gas, helium gas. So the atoms, these three gases, collision will be taking place between them. In order to avoid the exploitation of these gases, Brewster windows are arranged. These Brewster windows, they are designed especially at a particular angle. Next, the optical resonator is formed with two plano convex mirrors. One is fully reflecting surface, other is a partial reflecting surface. You can see the picture of this one. This is the figure. It's a glass tube we are taking, which is 5 centimeters long, 2 centimeters in diameter, and both the ends of the glass tube we are provided with two mirrors named as M1 and M2. They are forming the optical resonating cavity. And then these three gases, helium, nitrogen and carbon dioxide, these three gases are filled in the glass tube. And it is connected to a power supply. We need to give some discharge. So it is connected to a power supply. And at both the ends of the glass tube, you can see a dark line is given. That is nothing but Brewster window, because in order to avoid the exploitation, here we are designed, they have designed a window which is called as a Brewster window, which allows the gas atoms to collide with each other and not to produce any exploitation of gases. Okay, so this is the figure for this carbon dioxide laser. Next, what is the working process of this one? In order to explain the working process, we need to go for the energy level diagram. As I told you in the beginning, carbon dioxide has 4 energy levels. It has 4 different energy levels. Before these 4 energy levels, we are taking 2 other gases. One is called as nitrogen gas, another is called as the helium gas. So here let us show with respect to nitrogen gas and carbon dioxide molecule. Now nitrogen consists of 2 energy levels only. One energy level E1 and second energy level E2. As this carbon dioxide is having 5 energy levels with 4 energy levels, here we call it as a 5 energy level system, because the ground energy level we will not be considering that one. So here we have given it as E1 to E5. But basically carbon dioxide is a 4 energy level system. Remember that one. Okay, so this is how the energy level diagram is given. Now let me explain how the energy level diagram will be taking place. Now there are 2 possible types of transitions will be taking place. One transition is from E5 to E4, another transition is from E5 to E3. Now you can see, now we have pumped, we have released a gas, we have released a discharge. Then automatically that discharge will enter inside the glass tube. That is a quartz glass tube which is filled with the gases. That is, initially the energy is taken by the nitrogen molecules. Now the nitrogen molecules jump to higher energy state. Now through the process of collision, these nitrogen atoms, they supply energy for the carbon dioxide molecules which are in the lower energy state. Now the carbon dioxide molecules which are in the lower energy state, by absorbing the energy from the nitrogen atoms, they jump to higher energy state. In this one, as I told you, we have taken the ground state as a E1. So the highest energy state is E5. So through the process of collision, the energy is from nitrogen atom is given to the lowest energy state carbon dioxide atoms. Now the carbon dioxide atoms, they absorb the energy and they get excited to the higher energy state, that is the E5 state. Okay, next, from the E5 state, similar to helium and neon, here also there are 2 metastable states are existing. That one metastable state is from E5 to one metastable state is from E5 to E4, that is E4 is called as a metastable state, and from E4 the direct excitation will take place even to E3 also. So that's why the transition from E5 to E4 and the transition from E5 to E3, here we call the metastable states as E4 and E3. That means once when the atoms are getting excited to higher energy state, ఒకసారి కనుక atoms higher energy state లోకి వెళ్ళాయి E5 లోకి అంటే ఈక్వల్ నెంబర్ ఆఫ్ ఆటమ్స్ అనేటివి E4 స్టేట్లోకి E3 స్టేట్లోకి వస్తాయి. సో దట్స్ వై transition from E5 to E4 also produces a wavelength, also produces a laser output of a particular wavelength of 10.6 micrometers wavelength. That is the highest wavelength, because ఇక్కడ E4 స్టేట్లో మనం ఎక్కువ నెంబర్ ఆఫ్ ఆటమ్స్ అక్యుములేట్ అయినట్టుగా కొంచెం టైం ఎక్కువసేపు ఇక్కడ వెయిట్ చేస్తాయి. సో అగైన్ ఫ్రమ్ దేర్ the excitation will takes place direct from E5 to E3, because as I told you, E4, E3 రెండు మెటాస్టేబుల్ స్టేట్స్ ఉన్నాయి కాబట్టి E5 నుంచి E4కి కొన్ని ఆటమ్స్ డిఎక్సైట్ అవుతాయి. సిమిలర్గా E5 నుంచి E3 స్టేట్కి కూడా కొన్ని నెంబర్ ఆఫ్ ఆటమ్స్ డిఎక్సైట్ అవుతాయి. నెక్స్ట్ E4 నుంచి సమ్ ఆటమ్స్ విల్ డైరెక్ట్లీ గెట్ డిఎక్సైట్ టు E2 స్టేట్. ఫ్రమ్ E3 స్టేట్ ఆల్సో excitation to E2 state. So where you are observing more population, ఎక్కడ చూస్తున్నారు more number of atoms? More number of atoms in E2 state లో చూస్తున్నాం. So population inversion is achieved in E2 state when compared to E1 state. So here it produces 2 wavelengths. That is because E3, E4 రెండు మెటాస్టేబుల్ స్టేట్స్ ఉన్నాయి కాబట్టి ఎక్సైటేషన్ E5 నుంచి E4కి జరిగినప్పుడు ఒక వేవ్ లెంత్ ప్రొడ్యూస్ అవుతుంది. అది 10.6 మైక్రోమీటర్స్. ఒక వేవ్ లెంత్ E5 నుంచి E3కి వచ్చినప్పుడు 9.6 మైక్రోమీటర్స్ ఆఫ్ వేవ్ లెంత్‌న లేజర్ అవుట్‌పుట్‌ని ప్రొడ్యూస్ చేస్తుంది. దిస్ ఈస్ ఎ వెరీ హై పవర్‌ఫుల్ టైప్ ఆఫ్ గ్యాస్ లేజర్. Why? Because is here this is particularly used for cutting process of diamonds, cutting of diamonds, very big molecules. By using this gas lasers we can cut them. So finally here two types of outputs are produced, one from E5 to E4 10.6 micrometers and one from E5 to E3 9.6 micrometers. Next, what are the advantages of this carbon dioxide molecule? The construction of CO2 laser is very simple. Even though it is a gas laser, construction is very simple. The output is also a continuous one, as like that of helium neon laser. Ruby laser చూస్తే it is a discontinuous one. అదే helium neon laser వచ్చేస్తే it produces continuous output. సిమిలర్గా ఈ కార్బన్ డైఆక్సైడ్ లేజర్ కూడా కంటిన్యూస్ అవుట్పుట్ని ప్రొడ్యూస్ చేస్తుంది. అంటే ఇలా కంటిన్యూస్గా ప్రొడ్యూస్ చేస్తుంది. సో దిస్ ఇస్ అవుట్పుట్ ఫ్రమ్ దిస్ లేజర్ ఈస్ కంటిన్యూస్. నౌ ఏదైతే ఈ అవుట్పుట్ ప్రొడ్యూస్ అయిందో దాని ఎఫిషియన్సీ వెరీ హై. హీలియం నియాన్తో కంపేర్ చేస్తే కార్బన్ డైఆక్సైడ్ యొక్క హై పవర్, దట్ ఈస్ దీని యొక్క అవుట్పుట్ అనేది ఎఫిషియన్సీ విల్ బి వెరీ హై. It has very high output power. Very high output power is 10.6 micrometers of wavelength of output is produced. So next, the output power can be increased by increasing the length of the discharge tube. ఇంకా ఎక్కువ మీకు వేవ్ లెంత్ ప్రొడ్యూస్ కావాలి అంటే ఇందాక 5 సెంటీమీటర్స్ తీసుకున్నది 7 సెంటీమీటర్స్ కానీ 10 సెంటీమీటర్స్ కానీ తీసుకొని చేంజ్ చేస్తే, లెంత్ ఆఫ్ ద ట్యూబ్ చేంజ్ చేస్తే you can produce higher wavelength output also. Next, what are the disadvantages? Each and every laser will have certain advantages, along with that disadvantages కూడా ఉంటాయి. First one, the contamination of oxygen by carbon monoxide has some effect on laser action. Now here మనం నైట్రోజన్ గ్యాస్ని పంపించాం. నైట్రోజన్ గ్యాస్ని పంపిస్తే కార్బన్ డైఆక్సైడ్, అందులో కార్బన్, ఆక్సిజన్ ఉంది. సో ఆక్సిజన్ అనేది కంటామినేట్ చేస్తుంది కార్బన్ని, సో కార్బన్ మోనాక్సైడ్ గ్యాస్ని. సో దాంతో దెర్ విల్ బి సమ్ రస్ట్ ఫార్మేషన్ విల్ బి టేకింగ్ ప్లేస్. సో దట్ ఈస్ వన్ ఆఫ్ ద disadvantage, so which reduces the output power. Next, the operating temperature plays a major role in determining the output power. Operating temperature, మనం ఎంత టెంపరేచర్లో వర్కౌట్ చేస్తున్నాము అని డిపెండెంట్ పైన అవుట్పుట్ ప్రొడ్యూస్ అవుతుంది. నెక్స్ట్, డ్యూ టు హై పవర్ లేజర్ లైట్ యాక్సిడెంటల్ ఎక్స్పోజర్ మే డ్యామేజ్ ఐస్ సిన్స్ ఇట్ ఈస్ ఇన్విజిబుల్ టు అవర్ ఐస్. దిస్ ఈస్ ఎ వెరీ హై పవర్ అవుట్పుట్, 10.6 మైక్రోమీటర్స్ ప్రొడ్యూస్ చేస్తుంది. ఇది కనుక ఎక్స్ప్లోడ్ అయితే ఆటోమేటిక్గా మన ఐస్ విల్ బి ఇన్ డేంజర్ సిచ్యుయేషన్. We will not be able to see our eyes. That is the basic disadvantages of this one. Next, what are the applications? As everyone knows, the applications, basically it is used in medicines. Laser is used in eye surgery, used for the treatment of plastic surgeries, skin injuries, to remove moles, tumors developed in skin tissues. Next, it is also used in scientific field. Scientific field in counting of isotope separation and to separate isotopes of uranium. ఎక్స్ప్లాయిటేషన్లో యూస్ చేస్తారు. నెక్స్ట్, టు ఎస్టిమేట్ ద సైజ్ అండ్ షేప్ ఆఫ్ బయాలజికల్ సెల్స్. To estimate the shape and size of biological cells, we use this laser light. Next, they are used to create plasma also. Laser light is used to create plasma. Lasers are used to produce chemical reactions. When laser light కొన్ని gases పైన, కొన్ని molecules పైన పడినప్పుడు it produces some chemical reactions. Next, industry. Industry also, it is used in very huge thing. Lasers are used to cut glass and quartz. It is used to drill holes in ceramics. They are used to drill aerosol nozzles. Very different peculiar thickness nozzles will be there. So to drill a hole, this laser light will be utilized. They are used for the heat treatment in tooling and automotive industry. Now you want to cut anything, you will heat this by using laser light. You will heat that material and then you can use it for cutting. So you can see these pictures, how drilling is done, how light is allowed to go with respect to different types of styling process. These are some of the images which I have placed for the application part. You can see these also. Reconnaissance helicopter, laser missile, ground force, all these are the applications of laser. Next, let us go for the next topic. With this, we have completed lasers topic. In continuation with this one, the second part of this chapter, that is lasers, it is optical fiber. Now, what is an optical fiber? This optical fiber was being invented by John Tyndall. And what he did is he demonstrated that light can be guided along a curved stream of liquid. When liquid is passing through any medium, then you can allow light to pass through that one. That was the demonstration given by John Tyndall. Next, what is fiber optics? Basically, what is fiber optics? Now, fiber optics, it is also one branch of physics which deals with the study of propagation of information in form of light. You want to transmit signals. Nowadays, you are using wireless we are using. So, that wireless also carries signal in form of waves. Here, the signal which is carried out, that is, the information has to be carried out. That information is carried in form of light rays or modes through transparent dielectric optical fibers. You can see the picture of this one. This is how the signal transformation is taking place inside the optical fiber. Okay. Next, optical fiber is a thin and a transparent guiding dielectric medium or material which guides or transmits the information as light waves using the principle of total internal reflection. Basically, optical fiber, as you see in your houses, wires will be there, no? That is a very thin transparent wire. Nowadays, we are getting a very thin and a transparent sheet of this optical fiber we are getting. So, inside that one, so many components will be there. Now, to propagate the light into that optical fiber, the basic principle used is total internal reflection. Now, this is how the optical fiber cables will be there. On the roads, you will be seeing these optical fibers, big bands of all the optical fiber placed in one plastic and again dumped into another plastic. This is how we'll be seeing on the roads of the cities where optical fibers are found. Next, what is the construction of an optical fiber? What are the different components of an optical fiber? An optical fiber consists of three components. First component is core. Core is the basic component. Second component is the cladding. Third component is buffer jacket. Core. What is the purpose of this core? What is the use of this core? The purpose of this core is, say this figure, the core is this one. It will be in form of a cylindrical shape. Core is in form of a cylindrical shape with some diameter, very less diameter, cylindrical tube it looks like, and then it is prepared either by using the materials like plastic or glass or fiber. By any of the material you can construct, you can manufacture a core, and then the main thing is core only the propagation of light takes place. This is the heart of optical fiber. What we can say is this is the heart. మనిషికి ఎలా అయితే గుండె కంపల్సరీ అని చెప్తామో అలాగే ఆప్టికల్ ఫైబర్లో కూడా కోర్ అనేది మెయిన్ కాంపోనెంట్. ఇది లేకపోతే లైట్ అనేది ప్రాపగేషన్ జరగదు లోపల. ఓకే, సో కోర్ ఇస్ ది హార్ట్ ఆఫ్ ఆప్టికల్ ఫైబర్ త్రూ విచ్ propagation of light takes place, and it is prepared by using either fiber or plastic. Okay, now the next component is cladding. Cladding is a material which is also prepared by using either fiber or plastic or glass. Now this is surrounded by the main component, that is the core. This is surrounded by core. That means it acts as a protective layer. This cladding acts as a protective layer for core. Why? Because is when you are sending light పంపిస్తున్నాం మనం కోర్లో నుంచి, అది స్కాటర్ అయిపోతుంది. అలా స్కాటర్ అవ్వకుండా ఒక ప్రొటెక్షన్ లాగా protection laga, here we are using cladding surface. So cladding is acting as a protective layer which is also prepared by the same type of material, that is glass or plastic or fiber, and it is also in form of a cylindrical shape. Okay, that is the second component. Now what is the third component? Third component is the buffer jacket. Now when you see the season, winter season, everyone starts wearing 1, 2, 3, 4 types of clothes, because in order to protect it from this cold season, we will be using jackets. Okay, so similarly here also, in order to avoid a phenomenon called as aberrations. What is this aberrations? That is destruction in signals. Destruction in signals. In order to avoid the destruction of signals, we are using the buffer jacket. And generally this buffer jacket will be prepared by using silica type of materials. Buffer jacket will be prepared by using this silica type of materials. This buffer jacket acts as a protective layer for core and cladding. Okay, on this buffer jacket, so many types of layers will be present. As how I told you in the winter season, how you will be wearing one clothes on the other, sweaters like that thing. Similarly, here also, in order to protect, in order to make the signal propagate through the optical fiber properly, here buffer jacket is being utilized. You can see the picture of this one, this red color in front of that one, small narrow one, which is there, this one. This is called as core. Now this one is called as cladding. And see this one, this is the silicon coating, silica coating. This is the buffer jacket, other coating. All these layers are present. That means in order to avoid destruction in signals, we are using number of jackets are being covered on this one. So finally, optical fiber consists of core, cladding and buffer jacket. So core is called as the heart of the optical fiber through which propagation of light takes place. Now next is, we know the construction now. We have come to know the construction. Then what is the phenomenon which is involved in this one? How do propagation of light takes place? Now an optical fiber works upon the principle of total internal reflection. You have come across in your intermediate also this concept, that is total internal reflection. Now what is this total internal reflection? In order to study about total internal reflection, let us first see what is Snell's law. What is Snell's law? What is Snell's law? So that is ratio of refractive indices, that is mu is equal to sin I by sin R. This is the basic Snell's law notation. Mu is equal to sin I by sin R. What is I? I is called as angle of incidence. What is R? Angle of refraction or reflection. Mu is equal to sin I by sin R. That is the basic Snell's law. By using this one, by using this simple law, we can explain what is called as total internal reflection. Here, instead of representing in terms of mu is equal to sin I by sin R, let me represent it in terms of mu is equal to theta 1 by theta 2. Let me represent in terms of mu is equal to theta 1 by theta 2. Now, as I shown you in this figure, n is called as the refractive index of the denser medium. N2 is called as the refractive index of the rarer medium. Rarer medium is the upper medium, denser medium is the lower medium. Now let us take this one. This is an optical fiber. This is an optic axis. Now this is this one. So this is called as denser medium. This is called as rarer medium. Now let us take one light ray. This is the incident light ray, which is making certain angle of incidence as theta 1. Let us take it as angle of incidence as theta 1. Now, when it is incident, now let us take the condition that theta 1 is less than, let us take theta 1 is less than theta 2. First condition, theta 1 is less than theta 2. That is, where is theta 2? Now we have incident, we are incidenting an angle of light ray making an angle theta 1, and this light ray is passing into the rarer medium making an angle theta 2. Now let us take in the angle, let us take the condition, if theta 1 is less than theta 2, then we say that the light ray which is passing from denser medium enters into the rarer medium making an angle theta 2. Next, let us take the next condition. This is the optic axis. The second condition is, let us take angle of incidence is equal to angle of reflection, that is theta 2. That is, this is the denser medium, this is the light ray which is passing from denser medium, angle of reflection, and when this condition we apply, theta 1 is equal to theta 2, then the light passes, we call it as light grazes, Grazes, grazes. Grazes means it passes across the optic axis. It grazes across the optic axis when theta 1 is equal to theta 2. This is the second condition. The third condition is when theta 1 is greater than theta 2. We have come across the three conditions: theta 1 less than theta 2, theta 1 is equal to theta 2. Third condition is theta 1 greater than theta 2. Now the light ray is passing from denser medium, making an angle of incidence as theta 1. Now then under this condition, theta 1 greater than theta 2, the light reflects back into the same medium, making an angle of reflection as theta 2. See the three different figures. Under the case of theta 1 greater than theta 2, theta 1 is angle of incidence, theta 2 is angle of refraction. Then when the light ray is passing from denser medium, under this condition, the light ray enters into the rarer medium. So the second condition, when angle of incidence is equal to angle of refraction, then the light passes across the optic axis, that is, light grazes across the optic axis. Now let us take the third condition, where we want to study about the principle of optical fiber, that is theta 1 greater than theta 2. Then the light ray which is passing from, which is entering from the denser medium, will enter into the rarer medium, and then under this condition, it again comes back, it again reflects back into the same medium. So this property we call it as total internal reflection. Now what is that total internal reflection? Now, this you can also define in terms of critical angle. Now, what is critical angle? Critical angle, which we represented by the letter C. Critical angle is the angle for a given angle of incidence. For a given angle of incidence, if the angle of reflection, theta 1 is angle of incidence, and if the angle of refraction is 90 degrees, if the angle of refraction is 90 degrees, then this particular angle is called as critical angle. Critical angle means for a given angle of incidence, if the angle of refraction is 90 degrees, then we define that particular angle as critical angle. Now you can see the definition of total internal reflection. When a light ray passes from denser medium to rarer medium and angle of incidence is greater than critical angle, then the light reflects back totally into the same medium. This phenomenon is called as total internal reflection. You can see this third figure which I have shown you here, or you can see this figure also, where when light is passing from denser medium, again it is reflecting back into the same medium. This will be followed under the condition theta is greater than theta c. Theta 1 or theta is greater than theta c. So this phenomenon we call it as total internal reflection. So this is the principle on which an optical fiber works. So we have come across the construction of an optical fiber. Then what is the principle behind the functioning of an optical fiber? Next, let us go for what is meant by acceptance angle and numerical aperture. Now, conditions to get this we have come across. What is meant by acceptance angle and numerical aperture? Acceptance angle. Now, we know an optical fiber now consists of 3 layers. So, let us take the 2 important layers. One is core and cladding. Now, let us take an optical fiber. This is N1, this is N2, this is also N2. N1 is called as core, this is called as core, this is called as cladding. Similarly, this also is cladding. Okay, now this is called as an optic axis. Now, we are allowing light, we are incidenting light into the optical fiber. So, how much quantity of light, how much amount of light is entering into this optical fiber, we need to find out. In order to make the total signal travel inside the optical fiber. For example, we are saying hello. Hello is one signal. Now this halo has to travel inside the optical fiber, that is inside the core medium. So this halo has to be incident at what particular angle of incidence? What should be the particular angle of incidence value in order to make this signal travel inside the core medium? So that particular angle of incidence, we call it as acceptance angle. ఓకే. వీ నీడ్ టు ఫైండ్ ఔట్. మనం ఫైండ్ ఔట్ చేయాలి. ఇక్కడ ఒక ఆప్టికల్ ఫైబర్ తీసుకుంటున్నాము. దానికి కోర్ క్లాడింగ్ సర్ఫేసెస్ ఉన్నాయి. మనం ఒక సిగ్నల్ ఇవ్వండి. ఏదైనా సిగ్నల్. హలో అనే సిగ్నల్ ఇస్తున్నాను. ఇన్సిడెంట్ సిగ్నల్‌గా హలో అని ఇస్తున్నాను. ఈ హలో అనే సిగ్నల్ కోర్‌లోకి ఎంటర్ అవ్వాలి. సో ఈ కోర్‌లోకి ఎంటర్ అవ్వాలి అంటే దాని యాంగిల్ ఆఫ్ ఇన్సిడెన్స్ ఎంత ఉండాలి? ఆ పర్టిక్యులర్ యాంగిల్ ఆఫ్ ఇన్సిడెన్స్‌ని మనం ఫైండ్ ఔట్ చేయడమే, which is called as acceptance angle. I have given the definition. Acceptance angle is the maximum angle with the axis of the optical fiber at which light may enter to the optical fiber in order to propagate through it. So we need to find out that acceptance angle. Now for that, let us take this optical fiber. Now, so we are incidenting the light ray. Let us take this light ray is traveling from air medium. It is passing from air medium, and let us represent the angle of the refractive index of air medium. Let us represent it by the letter N0. Now, let us take this light ray is touching at some point A. Now, then once it is touching the optical fiber, that is the core medium, it enters into the core medium. It is passing like this. It is moving like this. It is entering into the core medium. Next, this core light ray, this is touching this point. Let us name this point as B. Now, I call this point B as core cladding surface or core cladding interface. What is meant by core cladding interface? Core cladding interface means this is a wall which is having both the refractive indices. It is a wall which is having a refractive index. If you see this side, it is having N1 refractive index. If you see this side, it is having N2 refractive indices. So it is nothing but it is having this point B is having both the refractive indices. That surface, I am calling it as core cladding surface. Now, once the light ray, when it touches this point, that is core cladding surface, automatically the light bends into the same medium. The light will reflect back into the same medium. Once when the light is reflecting back into the same medium means it is satisfying the principle of optical fiber, that is total internal reflection. Okay, now again if you take this as the initial point, then again it travels like this. It touches this point. Again this is a core cladding interface. Again it comes back into the same medium, that is the core medium. Again if it travels, this is how the propagation of light ray takes place inside the optical fiber, satisfying passing from core cladding interface and then satisfying the principle of total internal reflection. Is it clear how the light ray propagation is taking place? We are taking an optical fiber consisting of core and cladding surface with refractive indices as N1 and N2. Now, we are taking a light ray which is incident on the optical fiber, and this light ray is passing from air medium with some refractive index as N0. Then when it is incident, then it is passing through the core medium. Now, once it is passing through the core medium, it is touching the core cladding interface. Once it touches the core cladding interface, the light ray undergoes reflection into the same medium. So, once light ray is coming back into the same medium, we call that principle as total internal reflection. This is how the propagation of light takes place inside the optical fiber. Now, let us arrive at an expression for acceptance angle. Let us derive one expression because we need to find out what should be the angle so that halo signal will be entering into the optical fiber. Now for that one, let us draw a normal. Let us draw a normal, making an angle of incidence as theta. This is angle of incidence theta. Let us name something, this is C, something this is C, this is something D. Then if you see this one, you can see the clear picture of here. This is incident A, then B, then we are drawing a normal, making an angle of incidence as theta. This angle, angle of incidence is theta I. This is the angle where the light ray is reflecting back into the same medium, then this is the angle of refraction as theta r. Okay, this is how the propagation is taking place. Next, according to Snell's law. Now, see this one, this figure. Now, you can write the equation for sine theta. You can write the equation for theta. So, you can write it for theta r, what do you call? Sine of Snell's law, that is n1 sine of 90 minus theta 1 is equal to n2 sine 90. Okay, or alpha I is, this is what you are taking, theta I. You can write this as theta I is equal to, that is theta I is equal to 90 plus theta r. Theta r. So, here we have written it as, in terms of Snell's law, n1 sine 90 minus theta is equal to n2 sine 90. Now, the sine of 90 minus theta is, theta 1 is cos theta 1. So, n1 cos theta 1 is equal to, sine 90 is 1. So, that is equal to n2 only. Now, we can write the expression in terms of cos theta 1, that is n2 by n1. This is a simple mathematical form we are using. Now, go it in terms of, you have an identity, sine square theta is equal to sine square theta plus cos square theta is equal to 1. You can write the equation in terms of sine theta, that is root of 1 minus cos square theta. Same thing we are applying here. So, sine theta 1 is equal to, in place of this one, 1 minus cos square theta, I am writing this one equation. So, sine theta 1 is equal to root over 1 minus cos theta is n2 by n1, n2 square by n1 square. Now, you can write this equation as n1 square minus n2 square by n1 square. The same equation is written here. Okay, that is equation number 4. Now, you can see one equation, equation 2 and 3 from equation 2 and 4. Equation 2 is this one. So, equation 2 is n1 by n naught into sine theta 1. So, that this equation, from both these equations we can write sine theta is equal to n1 by n naught into sine theta 1. You can check this equation, that is equation 2. Sine theta naught is equal to n1 by n naught sine theta 1. This is equal to n1 by n naught, sine theta 1 is nothing but root over n1 square minus n2 square by n1. So, theta naught is equal to, we wanted to express it in terms of acceptance angle. So, theta 1 is equal to, or theta c is equal to, or theta naught is equal to sine inverse of under root of n1 square minus n2 square by n naught. Now, we are taking air medium. So, air medium always, the refractive index will be 1. Then you can write the acceptance angle as theta naught is equal to sine inverse of under root of n1 square minus n2 square. Okay, this is the derivation for acceptance angle. Now, next, let us express acceptance angle in terms of numerical aperture. Now, what is basically numerical aperture? We are saying that we are sending the signal, hello. So, this signal, how much quantity of signal is gathered inside the optical fiber can be expressed in terms of a special terminology which is called as numerical aperture. There is a particular terminology where we can express how much quantity of light is entered inside the optical fiber. That can be expressed in terms of numerical aperture. So, numerical aperture definition is sine of maximum acceptance angle. Numerical aperture, we write it as NA. NA is equal to, it is nothing but sine of theta c. What we have written the previous one, that is theta naught, sine of theta naught. Now, what is this one? NA, it is nothing but, if you take sine inverse of root over n1 square minus n2 square. This is a previous equation, you can check the equation, sine inverse of root over n1 square minus n2 square. So, this is nothing but, numerical aperture is sine of acceptance angle, sine of sine inverse that one. So, we can write numerical aperture finally as numerical aperture is equal to root over n1 square minus n2 square. So, this is the final equation for numerical aperture. So, here a small relation we need to express in terms of numerical aperture. So that is, if we introduce a change in refractive indices, if we are changing refractive indices value, that is N1 and N2, which we are representing it in terms of delta, delta is equal to N1 minus N2 by N1, then we can write delta N1 is equal to N1 minus N2 cross multiplication. Then take this value, substitute in numerical aperture. Numerical aperture is N1 square minus N2 square, A square minus B square. You can write A square minus B square as A minus B, A plus B. So N1 minus N2, N1 plus N2. Now let us take this N1 minus N2 is equal to delta N1 into N1 plus N2 is 2N1. So this is equal to N1 into root over 2 deltas, because how you will be getting this 2N1 is, we are approximating N1 N2 is equal to N1. If you take this one, then this one, let us take it equal to N1, N1 plus N1, so 2N1. So you will be getting 2N1, delta N1 into 2N1. So this will be N1, this is N1 square. So under root it is there. I'll take out N1. So you are left with root 2 delta. So relation between refractive index and the numerical aperture is Na is equal to N1 into root 2 delta. Okay, this is about the acceptance angle and the numerical aperture of an optical fiber. This is very simple. That is, how much angle we have to maintain in order to allow the total signal pass into an optical fiber. We are saying we are giving some signal. That signal has to totally go inside. For example, I am speaking on a phone with other person. He is in a village. I am in a city. Then I started speaking with him. I said, hello, how are you? He did not hear how. He got the word hello. How is missing? Are you? He got it. That is, signal is missing. So that signal should not miss. So for that, what should be the angle? That particular angle we need to find out. That particular angle is nothing but acceptance angle. Once if you find out a particular angle where light has to be incident, where light has to enter into the optical fiber, then by using that particular angle of incident, we can make the total quantity of signal travel inside the optical fiber. That is nothing but the acceptance angle. So we have arrived at the acceptance angle derivation. Theta is equal to sine inverse of root over N1 square minus N2 square. So this is about numerical aperture and acceptance angle. So with this, for this, the textbooks which you need to follow is applied physics textbook, any textbook, applied physics, because in Gaur and Gupta book also you will be able to see this optical fibers. It is a general topic, and the specialized book which is prescribed here is Palaniswamy textbook, and then textbook which is also designed by our publishers, that is a Spectrum Publications, and also the oldest scientist who has given all this matter is S.O. Pillai book. This is the famous book, Tamilian he is a, and Palaniswamy is the what you call the S.O. Pillai is a guide for Palaniswamy, and from him he has taken all the content, and the same book has been prepared by Palaniswamy. So these are the reference books which you can get the matter from this one, what I have taught you. So thank you. With this, today's session is completed. Thank you.